So whenever you're ready, you can try sharing your screen.
All right, so let me try to do that. So can you see my title page, which says
yes,
conformal removability is hard.
So let's wait a minute, and then
Sure.
I'll introduce you, and then we start, and then you have 30 minutes from the time you start.
That's fine. Actually, I'm trying to find my Zoom controls, which all right. So I'm just switching my tablet around into horizontal so I can write on it, make scribbles like this. Just let me know when you'd like me to begin.
Yeah, maybe so we are not so late. We can begin. So it's a pleasure to introduce our next speaker, Christopher Bishop from Stony Brook, and he's going to explain to us that conformal removability is hard. Go ahead, Chris.
Yeah, so this began about a year ago when I was talking to a graduate student, not one of my own, who had claimed to prove something which I didn't believe. Not that I didn't believe the statement so much, but I'd worked on this problem a lot myself and I couldn't do it. So I was a little resentful of thinking this student could. But I didn't tell him that. Instead, I had to actually go through the proof and find where the mistake was, which I did. But it got me thinking it would be nice to just have an explanation for why there couldn't be a simple solution to the problem. And so that led me into to thinking about that. And that's what I'm hoping to tell you about today. It's a topic that I thought about recently, and it involves some harmonic analysis, not very much. It involves some fractals, a little bit, not too much. And I think I can describe it in 30 minutes. And so that's what qualifies it for today's talk. Please ask lots of questions. I'm not monitoring the chat, and I have my video off. I'm just looking at my screen. So just break in and say something if you have a question. So the general idea is that there's this set of collection of things called removable sets in complex analysis. And we'd like to have, so these are just subsets of the plane. So we're in the plane and we have a subset, a compact set. And we'd like to characterize these, in terms of Hausdorff dimensions or measures or something to do with their shape. But this has, people have been working on this for decades, and there are some necessary conditions and some sufficient conditions, but no complete answer. And I try to explain to you why that is today. So the idea of a removable set is that if you have a set E in the plane, here's E, and you have some function F on the complement, which is holomorphic, and it has some property, like maybe it's bounded. Then we say the set is removable if you can extend the function by defining it on the set E so that it's holomorphic on the whole plane. So it's sort of like in calculus when we have a singularity of a function that looks like this versus one that looks like this. So this would be a removable singularity because we can just fill in the function and get a continuous function everywhere. And something like this is not, because there's no way of defining it on the set E. And so it depends on what this additional property is. So there's several different collections of sets. And it seems one of my pages seem to be blank. Technical issue. Okay. Let's try this again. All right. I'll have to write something in. One of my slides that came out blank. And then just hold on a second. I'm sorry. Let me just check something else. All right. So the four things that we're most interested in, the four properties, one is called H infinity. And so this is just being a bounded holomorphic function. Most people have seen this because there's when you take complex analysis 1, if you have a holomorphic function, which is bounded and holomorphic on a punctured disk, Then the Riemann removability theorem says that you can extend the function to be holomorphic through the puncture. And what this says is that a single point is removable for bounded holomorphic functions. Now, very famously, Xavier Tosa had characterized all the removable sets for bounded holomorphic functions rather recently, certainly since 2000. It's not really important what his theorem is. I mean, here it is. What it says is that you're not removable. So you have there's a holomorphic function on the complement which cannot be extended across E, if and only if the set supports some kind of measure mu that has a growth condition, it has most linear growth, and it satisfies some harmonic analysis looking condition, namely that something called the Menger curvature is an L2 with respect to this measure. This is the only slide where I'll mention this, so I won't give the definition. The point is that for H infinity removable sets, there's an answer. We know how to do the problem. If we take the property that we take holomorphic functions which are one-to-one, so now the property we're interested in is being one-to-one, which is called Schlicht in German, which is why these are called S removable sets. Those were characterized by Alfors and Berling. And again, I won't write down the exact characterization, but those two cases have been solved. Two cases that have not been solved involve when the function has a continuous extension to boundary. So it extends continuously to E. Those are called A removable. We don't have a characterization for those. And another case we don't have a characterization for is what we call CH removable. So this is for conformal homeomorphisms. And unfortunately, the slide where these were defined is not showing up. It was there 20 minutes ago. I just looked at it during the previous talk. So conformal homeomorphisms means that you have this set E, and on the complement, you have a holomorphic function which is one-to-one, so it's a conformal mapping on the complement, and it extends continuously. So I'm trying to write extends continuously very, very poorly here. And this one we also do not have a characterization for. So for H infinity, there's an answer. If you just have one-to-one, which is called Schlicht, there's an answer. If you just have the class A, which are continuous extensions to the boundary, we don't know the answer. We can't solve that. And if you have continuous homeomorphisms, which is a combination of these two, so it's one-to-one and continuous, we also don't have a characterization of those removable sets. So sometimes we can solve this problem and sometimes we can't. And there's a reason for this. And the reason is how complicated are these sets? So let's just think of compact sets in the plane. So we have think of the square, 0, 1, 0 to 1. And think about compact sets in here. There's a notion of the distance between two compact sets. If I have a compact set here, so the blue is one compact set and the pink is another one, each of these is within some epsilon neighborhood of the other one. And this defines the Hausdorff distance. The Hausdorff distance between two sets is just the smallest epsilon, so that each set is inside an epsilon neighborhood of the other one. And this makes the collection of compact sets in the plane into a metric space. And if we're just considering compact subsets of a compact set like the unit square, this is a compact metric space. And so you can ask about all the removable sets. So in the space of all compact subsets of the square, we can think of Tolsa's theorem. He characterizes which ones in here are removable for H infinity. And now we can ask, well, is that a closed set? Is it residual? Is it a G delta? Is it an F sigma? Is it a Borel set? Is it a not Borel set? How do the removable sets sit inside the collection of compact sets? And that's what I wanted to tell you about today. Okay, that's the general setup. Just to remind you, a G delta set is one which is a countable intersection of open sets, right? So you remember that if you have a point, that's a G delta, it's closed, but because you can write it as an intersection, a countable intersection of open sets, it's also a G delta set. An F sigma is a countable union of closed sets. And finally, we're going to be interested in things which are Borel or not Borel. Borel sets those are the smallest sigma algebra containing all the open sets. So if you've taken or taught a measure theory class, you probably talked about the Borel sets. And here, I hope on the next page is a collection of results. The collection of all the H infinity removable sets. So this is what Tulsa did. These are a G delta in the set of all compact sets. So it's not a very complicated collection. The set of removable sets for bounded holomorphic functions is a G delta in the space of all compact sets. This is what Alfors and Berling did. The S removable, these are the ones that were one-to-one, they're Schlicht. Those are also a G delta, okay? Then we get to the A removable. Those were the sets, those were removable sets for having the property that you're holomorphic and have a continuous extension to the boundary. We don't know how to characterize those. Well, that collection of sets is not a Borel set inside the compact sets with metric, Hausdorff metric. And similarly, the conformal the CH removable ones, so remember these were the one-to-one and continuous. It sort of combines 2 and 3 combined together, give you 4. Those are also not a Borel set. And so this is a partial explanation of why we can solve these problems, but we can't solve these 2 problems, because inherently the first 2 problems are easier. We're trying to characterize a G delta set. And in the second case, the ones that we haven't done, we're trying to characterize sets which we can prove are not Borel sets. And so I wanted to sketch the argument for why these are true. Okay. If I'm going to focus mostly on the second part here, why things are not Borel. People generally have a better idea of nice things like G deltas. Roughly, for example, to prove that the H infinity removable sets are a G delta, it basically boils down to a normal families argument, that if you have a set, if you have a sequence of sets En, and they are converging to some limiting set E over time, and if you have bounded holomorphic functions on the complement of the ENs, you can use normal families to extract a bounded holomorphic function on the complement of E. And then by passing to a limit and just, not doing very much, just a couple of sentences, you're able to prove that, that the collection of all removable subsets for H infinity is in fact a countable intersection of open sets. And so it's really just 3 or 4 lines long as the proof of that. Of course, Tolsto's characterization of what that G delta is, that was a very, very, very deep theorem. And it took many, many decades of work by various people to build up to. So just because it's a G delta doesn't mean it's easy to characterize it, but it sort of means that it's possible to do. Questions so far? I've said a lot. I said it pretty quickly. So please feel free to interrupt if I've said something too quickly, or can you hear me? Someone say something so I know I'm not talking to space.
Yeah.
Okay.
Everything is okay.
Everything's okay. I always worry.
I think your slides are a few seconds behind what you're saying, but I think it's not the problem.
All right. Well, yeah, as I said, at least one of my slides was a blank where I was expecting something to appear. And I had gone through my slides earlier to make sure they were all there. So there could be some Wi-Fi. I'm in a hotel, actually. I'm not using my usual Wi-Fi at the office or at home. So I'm on a trip right now. So how do you prove something is not Borel? So this is something which probably we don't usually cover in a first-year course in analysis. We don't worry about this too much. But the idea is that a continuous inverse image of a Borel set is also Borel. And that's because continuous inverse images of open sets are open. And then from that, you can it's not too hard to prove this, okay? And so basically, what you want to do is, if you're trying to prove you have a set E, which is inside a space Y, what you want to do is find a continuous mapping of some other X to Y and some set here, which maps to E, and F you already know is not Borel. So someone told you, you have an oracle that says that's not Borel. Well, if E was Borel and F was the inverse image of it, we'd get a contradiction. So the way to build non-Borel sets is to start with something you already know is not Borel and then take continuous images of it. Okay, and that's the strategy we're going to use. And fortunately, there are some well-known non-Borel sets. And we're just going to accept as axioms that these sets are not Borel. And so we don't have to, I won't prove that for you today, although the examples I'm going to use are not too hard. You can prove them in a couple of pages. It's definitely a textbook. Okay. Now I'll just make a historical note here. Inverse images of Borel sets under continuous maps are Borel, but forward images are not. In fact, we had a couple of graduate students lose some points on our Stony Brook comprehensive exam last year because they tried to use this fact, which is not correct. However, they were in good company because Lebesgue very famously made the same claim. He had a paper, and in his paper, he used the fact, well, the so-called fact, that continuous images of Borel sets were Borel. And one historian of mathematics cites this as one of the most fruitful mistakes ever made in the history of analysis. Fruitful because this is in 1905, and just a few years later, in 1917, a graduate student, Suslin, in Russia, discovered Lebesgue's mistake, and he constructed an example of a Borel set and a continuous image of it, which was not Borel. In fact, you can even just take a set in the plane and project it orthogonally onto the real line, and you can pass from a Borel set in the plane to a not Borel set on the line in this way. And so nowadays, continuous images are called Suslin sets or analytic sets in his honor. So it is possible for the graduate students to outdo the professors sometimes. So we professors do have to keep an open mind about that. Okay. So we're going to take, to begin with, the fact that closed countable subsets of the interval 0, 1 are not Borel in the set of all compact sets. So this notation, 2 to the S, in this talk, this means the compact subset of the expo power set. But I mean this notation just to mean the compact subsets of 0, 1. And so this is a pretty standard fact. And if you're interested, I can point you to some textbooks on real analysis, which prove this. And now the fact that that various removable sets are not Borel follows pretty easily. So there's a theorem of Fred Gehring that says if you take a set on the line, E, and you cross it with an interval, so you get a set sort of looks like this in the plane, then this product is removable if and only if the set along the base is a countable set. So if you take a countable number of points and take an interval, you get a countable number of intervals. And that is a removable set. That's small enough to be removable for continuous one-to-one holomorphic functions. But if the set is uncountable, if you have a Cantor set and you cross it with an interval, then it's definitely not removable. So it's an if and only if statement. Now, what that means is we have this mapping of E maps to E cross an interval. And this thing is removable if and only if E is countable. And the collection of countable sets is not a Borel set in the set of all compact intervals. So we have the removable sets are a continuous image of a non-Borel, of a known non-Borel set. So this is how we prove that the conformally removable sets are not a Borel set. And so Gehring did this back in 1960. So this is not a old theorem, or this is not a new theorem. It's an old theorem. This interpretation of it, I don't know if it's been made before, but the basic statement is correct. You do have to check that the mapping from E to E cross I is a continuous mapping in the Hausdorff metric, but that's not too hard. If you have an approximate set to E and cross it with intervals, it's going to approximate what it should. So crossing with an interval will preserve the Hausdorff distance. So that's fine. Now, Carlson, even earlier in 1960, Leonard Carlson in 1951, he had done it a similar thing for A removable. Remember, A removable was continuous extension to the boundary. CH was continuous plus 1 to 1. So this is a slightly different notion of a removable set. And what he had shown is that if you take a set E here, but instead of crossing with an interval, you cross it with a Cantor set F of positive linear measure. So you're taking a product of some unknown set E with a set of positive linear measure. He proved that was removable for the class A if and only if E was countable. So it's very, very much like Gering's theorem, except it's a slightly different property. It's continuous in 1-to-1 instead of just being, sorry, this is just continuous, and CH means continuous in 1-to-1. But in both these cases, there are old theorems from over 50, 60, 70 years ago, which say that these sets are not Borel, right? Now, the question that the student asked me a year ago was not really about any of these. What it was really about was Jordan curves. So what we're really interested in for dynamics and for various applications are when we have a closed curve in the plane, is it removable? That is, if we have a conformal mapping over here and a conformal mapping over here, and they match up along the boundary, do we get something that's conformal on the entire plane? Okay, so this is a problem that comes up when you're studying like Julia sets of dynamical systems or various other things, limits of declining groups. We would like to know which curves can be removed for CH. Now, what we'd like to do, one thing that seems like it might be a good idea would be to take Carlson's thing, which produced, remember, Carlson gave us a way of producing Cantor sets, which were product sets of one set here and one set here. And he gave us a characterization of when these product sets are going to be removable or not removable. Now, these are Cantor sets, not curves, but every Cantor set can always run a curve through a Cantor set. That's always topologically possible. And then this curve ought to be removable if and only if the Cantor set it's running through is removable. So it seems like the same proof that we gave for Carlson ought to work for Jordan curves. But it turns out when you try to write this down carefully, there are some technical difficulties. So the theorem is correct. You can prove that the Jordan curves, which are A-removable, do not form a Borel subset of all the Jordan curves. But you can't quite repeat what we did. In particular, instead of using the countable closed sets as your is a graph with no loops in it. I've drawn a picture here. It's convenient to think of a tree as a subset of sequences. For example, here is a branch of a tree, and we can think of this one as being, the vertices are labeled, and this corresponds, this branch corresponds to sequence 1, 3, 2, because I start with the empty set, I have a vertex labeled 1, and then 3, and then 2. And so if I delete this, I just get the sequence 1, 3, which represents the shorter edge. And if I delete the 3, I just get a 1. And so formally, you can think of trees as being subsets of finite sequences of integers that have the property that if you take any one of these strings and you remove the last element, what you get is another element. So trees are really just finite sequences of integers which are closed under the operation of removing the last element. And we're going to allow infinite trees. Okay. Now there's two ways, at least two ways, that such a tree could be infinite. It could be that you could have a vertex of infinite degree, and oops, I just switched pages by accident. I didn't mean to do that. You could have one vertex which has infinitely many children, that it goes on like that. We don't care about that. That's okay. We're fine with that. The other way that a tree could be infinite is you could keep going down, that there could be an infinite branch, so that There's an infinite sequence so that everything has a successor going down it. That's bad. We don't want any infinite branches. Trees that don't have any infinite branches are called well-founded. So finite trees are obviously well-founded, but there are other trees that are also well-founded. For example, if you just did this, so you have one vertex of infinite degree, and out of it comes finite length pieces. Well, there's an infinite number of edges here, but there's no infinite branches because every branch here terminates. And so this is a well-founded tree. And it turns out that the well-founded trees are not Borel in the space n-to-n of integer sequences. N to the n has a natural, you can make it into a complete metric space in a pretty simple way. So well-founded trees are a very famous example of a not Borel set inside a complete metric space. And lots of other non-Borel sets are gotten by taking continuous images of this. And that's what we're going to do in our, to get the Jordan curves. So we want a mapping that takes trees into Jordan curves so that well-founded trees map to removable curves. And I will show you a picture because this is harmonic analysis and fractals, and this construction sort of looks like it has some fractals going on. So let me just show you. Here's our building block, okay? So it might be a little bit hard to see here, but there's a curve that comes in here, and then there's a mystery box where we don't quite know what's going to go on. And then this curve continues and continues and continues all the way down here, and then it comes back up, and it comes back up, and then it comes back here, and then it comes down here, and it comes back up here, and then it goes all the way around here, and it goes down here, and does infinitely many things here, it comes back up, and goes out here. So this is a building block for a curve. And in these gray boxes, what we're going to do is put more stuff to build an even more interesting fractal-like curve. And there's only two things we do in the boxes. There's only two possibilities. The first possibility is that we could connect the two boxes up, that we just draw an edge that connects the two sides. So a box could just go like this. So the box could basically be empty. That's one thing that could happen. The other thing that could happen is that we could take this entire box and shrink it down and put the whole thing in here. So what we would get is a picture that looks like this. So it's a bit of a mess. But those are the only two things that ever happen in this construction, is that a gray box just gets crossed by horizontal lines, or the whole building block gets shrunk down in an affine way and gets placed inside one of the gray boxes. And then, of course, inside this gray box, there will be new gray boxes, infinitely many of them in this picture. And then we have the option of putting more copies of this thing into those. So these little boxes can then either be crossed, or you can fill in a whole copy of it. So it's kind of hard to draw more than one iteration of this picture. I'm sorry about that. I tried. I will show you a slightly better thing. Okay. Now, how does this relate to a tree? Okay. So basically what I'm showing you here corresponds to the empty tree that has no vertices. That's sort of the building block. And then each of these gray boxes is associated to integers. So these four boxes go with the integer 1. They're the first layer. As you come in from the outside here, these are the first boxes you hit. They're layer 1. If you get through layer 1, you get to boxes which are layer 2. These are all labeled 2. And then the 3 boxes are down this column, and there's some 3 boxes down here. And then the 4s are next, and all the way down to the limit. So, I mean, there's a layer of boxes here, which is 10 to the 10. It's very, very close to the edge. It's very hard to see that one, but they're all here. Okay. And when I have a tree, for example, if I just have the tree, well, let me show you. I've actually filled this in a couple of pages. So the easiest thing you can do, I said, you always have a choice. You can either just cross the box with 2 horizontal lines, or you can fill a box with a copy of the template. And suppose you never do that ever. You always just cross the box with straight lines. you get this tree. This is a picture of it. This is the tree empty. This is the empty tree. So it's the tree represented by the empty string with no vertices and no edges. And this is the simplest tree in our, this is the simplest curve in our collection. We basically always do the trivial thing and we never do the interesting thing, ever. Now, the next most interesting tree after the one with no vertices and no edges is the one that has one vertex and no edges. That's a pretty simple tree as well. So we just take the tree, which is one vertex. That vertex, say, has label 1. So in these boxes, you know, these boxes are no longer just nice gray shaded boxes. There's now a copy of the template which has been put in to all the label 1 boxes. But all the label 2 and 3 and 4 boxes have been left empty. There's nothing there. And what we do is we just fill them in with straight lines. And when we do that on the computer, this is the curve we get. And so the only difference between the empty tree is that we've now put copies of the template in these boxes, which were the 1 boxes. And so this is the tree, which is just basically has the strings are the empty string and the 1 string. This is the second most simple curve in our family. Well, this is the tree that has the empty set and then 2 children vertices labeled 1 and 2. And you can see I've made the template replacements in the 1 boxes, and I've also made them in the 2 boxes. And over here is a 1 box, and over here is a 2 box, and nowhere else have I done any replacements. Everywhere else I just use the straight lines going across. And so this is the simplest thing. Now, all of the things I've shown you are removable because there are Cantor sets in the limit here. So there's all these Cantor sets here, but there's only a finite number of them in these pictures, okay? And so the curve is made up of a countable number of line segments and a finite number of linear Cantor sets. And that turns out to always be removable. These are always removable. In fact, as long as there's only a countable number of these Cantor sets, it's going to be removable. And that always happens for well-founded trees. Now, if you don't have a well-founded tree, if you have an infinite branch in your tree, what it means is, suppose that you had a tree labeled 1, 1, 1, 1, 1 forever. At the first stage, you do the replacement here and here. These were the 4 boxes that were labeled 1. At the next stage, you're going to do replacements in each of these. So now you have Cantor sets here, 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 here. You have 4 of them. And then at the next stage, you'd split it again and you have 8 of them. And then at the next stage, again, you split and you get 16 of them. If you keep spinning forever, you get a Cantor set of linear images. And by Carlson's theorem, if you have a Cantor set horizontally and a positive linear measure set vertically, you get a non-removable set. And so this is how you prove the result, is that the tree is well-founded if and only if the curve that we've constructed is a Jordan curve. Now, this is just a warm-up because I really want to know this for CH instead. This is really the interesting case. And I just don't know how to do it. So this is my cry for help. Am I out of time, or do I have 2 or 3 more minutes to describe why I'm more interested in CH than I am in A? Anybody awake still?
Yeah, sorry, I was muted. Actually, you are out of time, but if you could keep it to 1 minute, go ahead. But otherwise, yeah, sure.
So I'm very interested in a problem called conformal welding. When you have a Jordan curve in the plane, you can have a Riemann mapping to the inside and a Riemann mapping to the outside. If you follow the map over and then back, you get a circle homeomorphism, a mapping of the circle to the circle. That's called a conformal welding. Not all circle homeomorphisms are conformal welding. Some are and some are not. And again, we can't characterize which are which. However, so I'd like to prove that the conformal weldings are not Borel, because then we would have an excuse for why we haven't been able to characterize them. And the point is that this mapping of basically given a curve, we get a circle homeomorphism. So we have a mapping from curves to homeomorphisms. which we can, let's just take my word for it. This is a continuous mapping. And it turns out that if, I say continuous images of Borel sets are not Borel, but it turns out that if you have a one-to-one image, that's a continuous image, then that does preserve Borelness. So a one-to-one continuous image of a Borel set is a Borel set. So if every curve gave us a unique conformal welding, at least modulo some obvious similarities, then we could prove that the conformal weldings were a Borel set, because the space of all Jordan curves is a Borel set. In fact, it's a complete metric space on its own. So it's Borel in itself. The problem is that the mapping from curves to homeomorphisms is not one-to-one. You can have two curves which are quite different. Maybe one has zero area and one has positive area, but they both have the same welding. And this happens when these curves are not removable for conformal homeomorphisms. And so the difficulty in characterizing conformal weldings boils down exactly to the problem that we were just discussing. Which curves are conformally removable and which aren't? And so this is the problem which I would really, really like to solve, or at least prove it's really, really hard, one or the other. And at the moment, I am stuck on that. But thank you for your patience. I don't want to run over, so I think we'll end there. I'm trying to advance to my thank you page at the end. You've been very patient. Thanks.
Hey, thank you, Chris, for a very interesting talk. Well, I'm going to ask the obvious question.
Okay.
So these non-Borel sets of removable sets,
Yes.
Are they Suslin?
Yes. So these, so I have a preprint posted on my webpage, which is mostly expository. The only non-expository part was this construction of the fractal sets. Try and turn my camera back on, but I can't seem to get the controls. But yes, so all the things we're talking about are in fact continuous images of Borel sets. And so they are analytic, they are Suslin sets. So that's one thing which I do show how to prove in the preprint. The preprint, as I said, it's actually goes through the history more. It gives more or less complete proofs of all these things. So all the things that I was accepting as facts and background, I actually discuss by copying from relevant textbooks.
Okay, so I think it's time to get ready for the next talk. So let's thank Christopher again.
Thank you.
And let's have